In this video, we will give an overview of graphing quadratic functions. A parabola is the shape of a quadratic function, and the turning point form is the most useful form when considering the transformations of a parabola. So if the value of a in this equation is greater than 0, the parabola is concave up, which means it will be this shape. And if a is less than 0 or negative, the parabola is concave down, which means it will be this shape. Key features of a parabola include the y-intercept, the x-intercept if they exist, the turning point, also known as the vertex, and the axis of symmetry, where the vertex lies on that. Finding key features of graphs is a useful way to graph parabolas. When a parabola is in turning point form, that is y equals a times x minus h squared plus k, it provides the most useful information about the transformations that have occurred to a parabola. So the value of a, which is this value here, causes a dilation by a factor of a from the x-axis. If a is less than 0, the graph is reflected over the x-axis. The value of h here causes a translation of h units parallel to the x-axis, so that's left and right across the page, but we need to be really careful with the language we use when describing translations. K causes a translation of k units parallel to the y-axis, so that's that value there. And again, that's up and down the page, but we use the direction of the positive y-axis and negative y-axis to describe that translation. Remember, you can always get a quadratic to be in turning point form by completing the square on the general form of a quadratic. And there's other videos that you can look up to find out how to do that. The correct order to consider transformations when it's in turning point form is dilations first, which is the value of a, then reflections, which is also the value of a, and then finally you consider the translations which occur parallel to the x-axis and parallel to the y-axis. And that's the values of h and k. So in the equation y equals a times x minus h squared plus k, the value of a causes a dilation by a factor of a from the x-axis. So that's going to stretch our graph up and down this way, making it narrower or wider, which you can see in the animation below. If a is less than 0, the parabola will be reflected over the x-axis, so that's when it changes from concave up to concave down. So as a note, visually, a dilation will cause the parabola to be wider or narrower than the original graph. So if a is between 0 and 1, the graph will be wider, and if a is greater than 1, it is narrower as the graph is rising more steeply, as you can see on the dynamic graph given. In the same equation, h will cause a translation by h units parallel to the x-axis. So if h is less than 0, the graph is translated in the positive x direction, and if h is positive, the graph is translated in the negative x direction, which is shown on the dynamic view below. So as a quick note, when describing a translation, you cannot use the language of left and right. You have to use the language of positive x direction and negative x direction. In the same equation, the value of k causes a translation by k units parallel to the y-axis. If k is less than 0, so k is negative, the graph is translated in the negative y direction, which is down on the set of axes. And if k is greater than 0, making it positive, the graph is translated in the positive y direction, or up. So once again, when we describe a translation, we cannot use the language of up and down. Instead, we need to use the language of the negative y direction for down and the positive y direction for up. So if we want to graph a quadratic, we can use the following general method to do that. So the first thing you want to do is find the y-intercept. To find the y-intercept, we let x equal 0 and solve for y. To find the x-intercepts, we let y equal 0 and solve for x. This is most easily done when it's already in factorized form. Alternatively, you can use the general quadratic formula to find x-intercepts, and the discriminant can be used to give information about the number of x-intercepts. And here we remember that the discriminant, delta, is equal to b squared minus 4ac, where the values of a, b, and c come from the coefficients of x squared, x, and the constant term in the general equation. We then need to find the turning point. So this can easily be found if it's in turning point form. So if it's in the form y equals a times x minus h squared plus k, the turning point is at hk. Alternatively, the turning point exists on the axis of symmetry, which is x is equal to minus b divided by 2a, And again, A and B come from the coefficients in the general quadratic form. After we've found these three key features, we need to plot the coordinates of those key features on a set of axes, and we need to make sure that we label all of these key features with their coordinates. Finally, we draw a parabola through the plotted coordinates, and it's very important to make sure your parabola looks like a parabola. The shape's important. So if A is greater than 0, it's going to be concave up, something like this, and if A is less than 0, it's going to be concave down, or something like that. Note that this method for graphing quadratics will differ depending on what equation you start with. So depending whether you're given general form, factorized form, or turning point form, you need to be flexible in how you use this method to find all the key features and plot the graph. So after this section, you should be able to determine the coordinates of key features of a quadratic graph, including the y-intercept, the x-intercept or intercepts, and the turning point. You should be able to sketch a parabola using key features when given any form of the quadratic. So you may be given the general form, the factorized form, or the turning point form. And no matter where you start, you should be able to find all the key features of the graph from any of those three forms.